hear me? Okay, great. So I'm not as eloquent as the previous speakers, so I'll just endorse everything they said, and also especially thank you all for your incredible warm hospitality. I'm very happy to be here. All right, so I was told this was a general talk for condensed matter and the entire physics department, but hopefully it looks like everyone here is mostly in condensed matter, but maybe for a few minutes you'd like to hear a little bit about black holes. All right, so okay, so I'll begin with just recalling a few basic facts from history. So first of all, you'd be very surprised to hear that quantum entanglement started in 1865. What I'm referring to is this quote from Kekule's spooky dream, who came up with the structure of the benzene molecule. And as you all know, benzene is really an entangled state of 6 electrons because there's 2 possible configurations that give it its perfect hexagonal shape. But anyway, as the quote says, and you'll see why I'm giving you this quote later, that he came upon the ring shape of the benzene molecule during a daydream of a snake seizing its own tail. All right, but of course, quantum entanglement really can be really began in 1935, this famous paper of EPR, where they proposed the EPR experiment, where you have electrons not entangled just in a single benzene molecule, but macroscopically separated, leading to what we call spooky action at a distance. And let me assure you that is something Einstein said in a letter to Max Born, in German though, but I'm sure that's given the audience who can verify that Einstein was speaking about spooky actions at a distance. All right, so that's a quick introduction to the first word in my title. Now, what is superconductivity? This was indeed discovered in 1911 by Camerleonis. This is low temperature superconductivity in mercury, but my interest really is in the discovery in 1986 of the cuprate high temperature superconductors, which are layered materials, and mentioned by a few of the other speakers. And for everything I'm going to mention here in this talk, you can just think of this as a single layer of copper and oxygen atoms. And as you know, this goes superconducting at liquid nitrogen and even higher temperatures, and has very interesting properties. And perhaps most exciting, these are words from a web page of a company, so please take them with the appropriate grain of salt. But I think this is less of a grain of salt than many companies you've seen recently. So this is an actual company, and there are several others. This is in Boston, where they're making magnets of yttrium-barium copper oxide. That's what this copper-colored material is. And the idea is that because of the improved properties of these materials, you can operate plasmas at a very different operating point in a smaller system, and maybe this will lead to fusion energy. So this is enough reason for me to really consider this a very important system to understand that. All right, so here's a little more detailed phase diagram that I'm sure all of you've seen as a function of density of electrons in that square layer and temperature. My focus here in the limited time I have will be only on the region that's not superconducting, for the simple reason that if you want to understand why this temperature here is as high as 100 Kelvin, well, we can only understand it if we understand the state it comes from. And what is the state that it comes from at the highest temperatures? Well, if you look at the lower temperature region, you find its properties are rather similar to a copper or something, and if you look at electrical properties. But you have much stranger properties here, exactly where the TC is the highest. In particular, one of the most celebrated properties, which is strange, is the linear in temperature resistivity, which extends over a very large temperature range, and is found universally in not just the cuprates, but many other materials, especially where you have the highest TC. So by the end of my talk, I will give you our current understanding of what this is due to and related properties. But before I get there, so why is this strange? Why is this linearity strange? Well, here we have to go back again to Weizmann, whose idea is really at the basis of our theory of metals. One of the things that he discovered, which is on his gravestone, and again you'll see why I mention this later, is the famous Weizmann formula between entropy and the number of states available to any system. This also applies to quantum systems where W is replaced by the density of all many-body quantum states. But for metals, Weizmann's insight was really the Weizmann equation, which he wrote down for a classical gas, like the molecules in this room. It's a dilute classical gas. But the remarkable thing is, as emphasized by Landau much later, is that the Weizmann's equation applies even for equally well for a dense quantum gas. And the reason are these factors here, these 1 minus F factors on the right-hand side, which impose the Pauli exclusion principle. And the effect of these 1 minus F factors, which are absent or really equal to 1 in a classical gas, is that collisions in a dense quantum gas are rare, because any particular single particle quantum state is either empty or full. If it's full, then this 1 minus F is 0. If it's empty, then the F is 0. So it's only at the boundary of occupied and unoccupied states, which is the Fermi energy, where you have any appreciable collisions. And it's this rareness of collision that allows us to make the key approximation that you think of collisions as independent of each other. This is something Weizmann called the molecular chaos assumption. But in a quantum system, you're also neglecting quantum interference or entanglement between successful collisions. And that's really the basis of almost everything in the theory of metals and semiconductors, other than fractional quantum Hall states that are being studied here, of course. So one of the consequences of Weizmann's equation is that the resistivity of a metal with a few impurities should increase as temperature squared at low temperatures. And this is observed in many, many materials. And it's, of course, this violation of this basic law of the Weizmann-Landau theory is why this metal is called a strange metal. But now you can ask, suppose I took Weizmann's theory and somehow manage to increase the collision rate between the electrons, when will it fail? And you can make kind of a energy time uncertainty argument that will fail when this tau becomes of order what people now call the Planckian time, which is just Planck's constant divided by temperature in units of energy. And as long as this tau, the collision time between collisions, is bigger than h bar over kT, then you can make the assumptions necessary to apply Weizmann's equation. So now I come back to the cuprates. I showed you previously this linear temperature resistivity. Now, linear temperature resistivity can come from many reasons, including some very low energy sets of phonons can give you this for not very interesting reasons. But a much more important and subtle property comes in the optical conductivity. So by measuring the reflectivity of one of these materials, you measure the frequency dependent of conductivity. Now, the Drude formula is exactly this formula here, where this mass, m star of omega, and tau of omega are constants. But when you do this here for the cuprates, you find they're far from constants. And in particular, 1 over tau of omega is in fact a linear function of frequency over a wide range of frequencies. And then when you scale the vertical axis by temperature, it also is a linear function of temperature. So in fact, you can summarize all of this data in this very beautiful formula that the frequency-dependent scattering time is given by exactly the Planckian time where the Weizmann theory must fail. And this is quite remarkable because the strength of the interaction, the fact that the repulsion, the Hubbard U is about an electron volt, it's not important at all. It doesn't come into a scattering time. Another thing that will never happen from Weizmann's equation, because in Weizmann's equation there is this T that I mentioned here, which depends on the strength of the interactions. Okay, so you get this universal tau of omega, which just given by fundamental constants of nature, the frequency and temperature. So quite a remarkable behavior that you see in several compounds and in most detail studied in this particular material. I think this is lanthanum structure, copper oxide. No, it's white. All right, black holes. And you'll see why I'm talking about black holes in a few minutes. Okay, yeah, I'm doing okay. So black holes discovered in 1916 as a theoretical prediction of Carl Schwarzschild, who said that solving Einstein's equations of gravity, that if you took a mass m and squeezed it to a radius smaller than what we call the Schwarzschild radius, then the gravitational attraction would be so strong that any light or any other matter could never escape the horizon of a black hole. And this is the incredibly dense matter. For example, for the Earth's mass, the Schwarzschild radius is less than a centimeter. So this seemed rather absurd that matter would behave this way, but of course I don't need to tell you, it does. There's a supermassive black hole at the center of every galaxy, with masses of several million solar masses. However, things are even more absurd than that. If you take Einstein's equation, the matter continues to collapse even after it has formed a black hole, and really you get a singularity at the very center. So of course, when things become so dense, we don't know what's going to happen, but clearly everyone would agree we have to use the full quantum theory of quarks and strings or whatever to really know what's going on inside a black hole. However, that's all classical physics. We normally think about quantum physics of black holes for the reason that it's truly important at the center. But the key insight came from Bekenstein and Hawking, who realized that you could actually understand quite a bit about black holes by just thinking about what they look like from the outside. In particular, if I take an EPR pair of electrons and separate them so that one is inside a black hole and the other is outside, then you still have entanglement, quantum entanglement across a black hole horizon, even though classically they can be nothing shared between the inside and the outside. So this type of reasoning, although not exactly this is a more modern understanding of it, led Bekenstein and Hawking to propose that black holes have an entropy and a temperature, because as an observer outside, having one part of this EPR pair, this qubit in my hand is effectively random, because I'm never going to know what any observer inside the black hole has observed. For this, it's really past my domain of information that I can get. So it's essentially a random qubit, and randomness, as Weizmann taught us, is entropy and related to temperature. Of course, that's a very simple argument, but it allows us to understand the Bekenstein-Hawking formula, which relates the entropy of a black hole to the area of its horizon and fundamental constants of nature. Because the entanglement is all happening right at the surface, and so if you view the thermal entropy of a black hole as really the entanglement entropy across the horizon, then it's very natural to understand why it's proportional to the area. And this is, again, was a shocking development as proposed first by Bekenstein, that these black holes should have an entropy proportional to the area, because all other systems have an entropy proportional to their volume. All right, so this has led to a basic problem, which you can summarize by these two famous gravestones, one of Weizmann and the other is Hawking's gravestone in Westminster Abbey. Which is, are these compatible with each other? That Weizmann told us that entropy is the log of the number of quantum states, and now Hawking has told us what the entropy is. So what are these quantum states? Can you make any sense of this and reconcile these two basic results of physics, both advertised on gravestones? All right. So why am I telling you all this? Well, it turns out there is a connection between the Planckian dynamics that I showed you for superconductors in the normal state and black holes, because if you take a black hole and you perturb it a little bit, and you ask how long does it take before it settles down into a perfect sphere at some fixed temperature, well, that time is called the ring down time. In fact, been measured by LIGO and other observatories. Is also predicted by Einstein's equations and the Hawking temperature expression here to be just the Planckian time. So this, at least for me, was a hint. First hint that there's some connection here between non-quasi-particle dynamics, where Weizmann theory breaks down in strange metals, and the very complex entanglement that's present in black holes. All right. So to make this connection, which turns out to be much more precise than I had ever imagined in the early days, we need some simple solvable model of quantum entanglement, complex quantum entanglement. And of course, that's my favorite model of quantum entanglement. So let me describe it, but let me refer back to Kekule's spooky dream in 1865, so to explain what this is. So I decided I had to have a spooky dream. And this spooky dream is based on the Indian game of snakes and ladders. Now, I show this in America, and nobody has any idea what I'm talking about.
We know.
So the British, yes. I did some Googling this morning, and I discovered in Israel you know what snakes and ladders. The British changed it to chutes and ladders. And when I showed this in America, everybody knows. Anyway, this is the game I used to play as a kid. And really, just to show this is to, first of all, say, imagine you had, as in Kekule's dream, entanglement, which was kind of random and between all different positions. And that's really all the SYK model is. So here, let me describe it pictorially. You take a bunch of quantum states. These are not necessarily localized as shown in this picture. Give them some labels. And you demand that all the states, there's no dispersion. So this is kind of like the flat band that Alan was referring to. And then you allow them, you occupy them with electrons, but you don't allow them to move on their own. If they moved on their own, this wouldn't be a flat band. But you allow them to interact in pairs, let's say. So for example, the electron on site 11 and 12 would interact and tunnel to sites 5 and 14. And associated with this interaction is a specific number. So now for the kind of models that Alan was talking about, this is a number you compute by knowing something about the flat band and putting in the Coulomb interaction. But what I'm going to assume is that all of these numbers, the n to the 4th numbers, for interaction between any initial site and any final site, are independent random numbers. Because that's what you need to be able to solve the problem. If I take some regular pattern beyond about 20, 30 electrons, we have no way of solving such a problem, except maybe in a quantum computer someday. But it turns out quite remarkably that if you take these numbers to be independent random numbers, you can solve it. We initially solved it in the large n limit, and now with the help of Kitev and many string theorists, we know a lot about all the structure of the finite n directions. So that's the model, and it turns out to leave a soluble model of multi-particle quantum entanglement, and one can show that it has no quasi-particle excitations, and if you were somehow able to move the fermions in this particular model, they're not going anywhere, they're just randomly hopping in pairs, that the current would be not carried by individual electrons, as they are in Boltzmann's equation or Landau's equation, but by some entangled quantum soup. So this is also more radical than the fractional quantum Hall effect, where the current is carried by fractional quasi-particles. Even those don't exist here, there's nothing, it's just an entangled mess. So what are some of the other properties of this entangled soup of fermions? So here's the Hamiltonian written out for those of you, I'm sure everyone in this audience knows. So the main assumption that these are independent random numbers, and their root mean square value is u. So the easiest way to solve this, which is the way we did it initially, actually no, we did something better than this, but the easiest way to see what the solution is just by a single particle Green's function and a Feynman graph expansion in u, and you average order by order. Then you get these equations here, which this is just Dyson's equation. This tells you the self-energy is the cube of the Green's function. And when we wrote this down in 1992, I thought, well, just a couple of months of work and we can figure out what the properties are. Yeah, we figured out a few, but we're still learning more. In fact, hiding in these very simple equations is information about quantum gravity, at least in low dimensions, as I'll indicate. Okay. Anyway, so what did we learn about these equations way back when? Well, first of all, there's some, this we understand later, but this benefit of hindsight, the equation has some special features due to some emergent symmetries. And the emergent symmetry is a time parameterization symmetry and a conformal symmetry. And one of the things you find from there is that you get this precisely this Planckian dynamic. So this particular model, although the details are quite different of this function f, for example, is precisely the type of Planckian dynamic that you see in optical conductivity of the cuprates. And modeling this type of dynamic was very much the motivation in 1992-93 for me proposing this model. We also now understand a little bit about low energy density of states. And they have this rather peculiar feature, which is that this is a numerical plot of the many-body density of states, that you get a zero temperature entropy without an exponential ground state degeneracy. So previous to this model, we had examples like the ice model of Pauling, where you had a whole bunch of exponentially large ground state degeneracy, and that gave you a violation of the third law of thermodynamics because the entropy didn't go to zero as temperature goes to zero. So here the entropy does not go to zero as t goes to zero, provided you take this order of limits. You first make the system very large and then send temperature to zero. So this is non-zero, and in fact a universal number we can compute. But there's no degeneracy. The ground state just has one state, two states. The point is that there's an exponentially large, small level spacing down to the ground state. And that's quite exceptional. And it turned out to be the key to its connection to black holes. All right, so the density of states is exponentially large, but there is no degeneracy. All right, so this I'll very briefly mention. I just added this I was listening to the other talks. There's a beautiful experiment by Phillips and group, in particular by Laura Anderson, when you took a little quantum dot, a graphene quantum dot in a magnetic field, and measured its thermal and electrical conductance properties, and they're in some flat band, and there's some randomness because of just the random shape of the quantum dot, and there are a number of properties that I don't have time to go into that match the physics of SY. It'd be great to really study this much more carefully. All right, so now I've described the SYK model. Now let me go back to the beginning of my talk and show you how it's helping us, or it's helped to understand some of these puzzles that arose both in superconductivity and in black holes. So first, let me talk about black holes. So if I was very naive and you gave me a black hole and I wanted to compute its quantum theory, what I have to do is take the action for gravity, the Einstein-Maxwell theory, say, and do the complete path integral of the metric and the gauge field with the 1 over h bar over there. All right, so nobody knows how to do this even today, but it turns out we've learned much more about this path integral for the case where the black hole has a net charge q. So this is the integral I want to do, and it's in 3 space and 1 time directions. There's the 2 space directions of x, which is the angular direction. There's the radial direction zeta, and there's time. So here's one picture of the black hole in real space. And here's another picture of the black hole that people draw in imaginary time. So now this direction zeta is the same as that direction zeta. The direction x I'm not showing you because it's every point. And in this two-dimensional space of zeta and imaginary time, the shape of the black hole is actually a cigar. In imaginary time, there's no inside, there's only the outside. And so all the problems with the singularity, the inside, you don't have to worry about. You just evaluate the partition function on the outside. And temperature and h bar appear from the fact, as we know, that time is periodic with time h bar over time. All right, so this is the path integral, in fact, that Hawking started to evaluate, Gibbons and Hawking. And they evaluated in the saddle point approximation. But now we know how to do it much better for the case of a charged black hole. So why is that even possible? Well, the reason it's possible is that it turns out for a charged black hole, and not a neutral black hole, unfortunately, you can reduce the path integral from 3 + 1 dimensions to 1 + 1 dimensions. You can just forget about the angular direction and just do the path integral for fluctuation in the zeta tau plane. And this leads to a path integral in 1 + 1 or two-dimensional quantum gravity called JT gravity. You can derive this from here to there. It's just a simple dimensional reduction. And then the remarkable thing is that through an application of some type of holography, because two-dimensional gravity is kind of simple, you can reduce it to a 0 dimension plus 1 dimensional integral, where the integral is only on the time direction. And the amazing thing is this action and the subsequent integral can be done exactly, and it's exactly the integral you would get starting from the SYK model. So I can start with the SYK model, set up a path integral representation, go to low energies. I can start with the Einstein theory, do this dimensional reduction, go to low energy. You get the same expression. So this allows you to then compute something about the partition function at least at low temperatures and energies for charged black hole essentially exactly. So let me just give you the answer that came from many years of work. There's the exponential factor, which is just the same as the Bekenstein-Hawking result combined with Weizmann. But now the knowledge of the SYK model has given this energy dependence. And in fact, this is a plot of the density of states of the SYK model, which also has exactly the same Sinch factor. The fact that our universe is not exactly an SYK model only affects this pre-factor which was computed last year. Anyway, so this is the answer, and this turns out for a charged black hole to be an explicit realization of this remarkable state of matter where you have a zero temperature entropy, extensive zero temperature entropy, but no ground state degeneracy. And this is in striking contrast to what happened from string theory or any supersymmetric theory, where you do get exactly that fact that they have a zero temperature entropy and a ground state degeneracy with this factor e to the s. It's only the complexity of the entanglement in the SYK model that's shown you that actually you don't get that, you get the Sinch square root of energy factor. Anyway, okay, so that's the same statement. So it's like a quantum, the SYK model is not actually inside a black hole, but it's a simulation of what's inside a black hole at low energies to an outside observer. Okay, if there's any string theorists here, they can correct me if I made something, said something wrong. All right, so I guess I have 2 minutes, 5 minutes. All right, I think I do it. Okay, finally, let me close the loop and go back to high temperature superconductors, which is, it was a happy accident for me that I didn't know anything about black holes in '93. But slowly I started learning about them. But my original love, of course, is this phase diagram. So, can we say something about this strain matter? Well, we need to know a little bit more about the specific microscopic physics of this material and other related materials. They're not SYK models for sure. But can we, given that we get Planckian dynamics here and in the SYK model, can we learn something and come up with a more realistic description of this material? And that's been my hope since '92, and I think recently we have made some progress that I just want to close my talk with. All right, so what we know is, I want to say something about the Fermi surface, which we can measure in photo emission experiments. So what we know in the ordinary metal is that the Fermi surface is exactly what you'd expect from Weizmann-Landau theory. You can just treat the electron as free, and this is the boundary between the empty and occupied states, just as would be the case for model of free electrons. On the other hand, at low doping, you don't see that. You see some state that people call a pseudo-gap state. Pseudo-gap because there's no excitation, no low energy excitation in this region. And what it is, well, I'm going to just sidestep that question given the short time available, but I'm happy to discuss that in much greater length with you later. But let me just make a few remarks about the general setup. So once we agree that the most important thing here is the fact that there are two different metals. And at zero temperature, maybe the strange metal will disappear. And you could somehow hide the superconductivity, then you'd have a quantum phase transition between, which involve a change in the Fermi surface. So let me just get rid of the superconductivity and set up this kind of generic quantum critical phase diagram, where you have two different Fermi surfaces with a zero temperature quantum phase transition. And this is, you can associate, so we have many models of such phase transitions, I guess, involving various broken symmetries, and even cases where there are no broken symmetries. And all of these models involve coupling the Fermi surface to some scalar field and possibly other fields. So the important thing for my brief discussion is that there's a tuning parameter S, which is like the mass of this boson, and a Yukawa coupling G between the Fermi surface and this boson. All right, so once you have the zero temperature phase transition, you have something very strange going on at the critical point, and possibly often at finite temperature. So what we know from 20 plus years of work is that in fact at zero temperature, at that critical point, you do have a very interesting state of matter where you have no quasi-particles. So that's similar to the SYK, but it doesn't have any zero temperature entropy or anything like that. But we need to understand quite a bit about it. And this has led to the hope that once we understand the zero temperature state, that we will also understand the strange metal as a manifestation of the zero temperature criticality at finite temperature. But slowly in the past decade or so, it's become clear that's a misplaced hope. If you take a perfectly clean system, which is describing this quantum critical point, in fact, the finite temperature state is a perfect metal. It doesn't show any of the characteristics that I described from the experiments earlier. So what's the missing ingredient? So here's a little more detail for the theory. You have the Fermi surface psi, you have this mass for the boson, and then the Yukawa coupling. Well, the missing ingredient is impurities. And so let's add some impurities. Well, the way you normally add impurity in the theory of metals is as a potential for the fermions, which you have to do here too. Now, what happens in the usual Boltzmann theory is you have sort of elastic scattering that comes from here, and then you have inelastic scattering that comes from electron-phonons or electron-electron, and then you use Matheson's rules to just add them up. So here, you can't do that. You cannot just treat them as independent and add them up. You really have to take the whole thing self-consistently. And in particular, there's another term here, which is the random Yukawa coupling that's really key. And when you solve this theory in the same sort of methods that we solve for the SYK model, so this is what we call the 2D, it's two dimensions, and the Yukawa SYK model, you get exactly what's observed, at least qualitatively. This is the resistivity as a function of temperature for various doping. This is the resistivity exponent plot. This is the optical conductivity, real and imaginary parts at different temperatures. This is what we get from our theory, very similar. And finally, of course, the main result that I advertised, this Planckian dynamics, now comes out also in this model, but in a much more realistic and hopefully even quantitative realization of the microscopic physics. All right, so to conclude, the main point of the SYK model, it gives you finally a handle on complex quantum entanglement in a regime where there are no quasi-particle excitation. There's no laughing quasi-particles, there's no electrons, there's no spin-ons, holons, whatever. There's just complex entanglement. And some 2D version of it seems to capture some key aspects of strange metals, and this is something we continue to work on. And somewhat surprisingly, the SYK model turns out to be just the ticket to really understand the generic structure of non-supersymmetric charged black holes. Thank you.
Anybody have a question? Okay, so I think that we should thank the four, all the speakers today who came, and it was a good time. Thanks you very much.